to take this technology to the next level and hopefully be able to provide some of those, give some of those abilities back to our veterans that they have lost. So the field of research that I'm going to be talking to you about today is called neuroengineering. And this is a relatively new field of engineering that is related to interfacing with electronic devices to the brain. So this involves being able to control things, control devices by thinking about that, or also being able to feel things that a sensor or a device actually picks up. And so what I'm going to do today is kind of give you a quick outline of where the current technology is, where we're pushing it, and some of the other possible applications that we could see of this field in the future. So the work that I primarily do is involved with movement disabilities. So people who have been paralyzed, who have had limbs amputated, they lose this ability to perform a certain kind of movement, and that's what we're trying to restore. Whether that is through the use of different types of recording devices that can actually listen to the brain, or other types of devices that can actually stimulate the brain. So we're just going to jump in here. So before we jump into what this technology actually is and what it all means, we got to first understand some very basic things about the brain. So the brain is this it's a little over 3 pounds of mush, basically, that sits in your head. And it's honestly one of the most, arguably the most complex structure that we've ever seen in the entire universe. The brain is primarily composed of individual cells called neurons, and these neurons are connected to each other through trillions and trillions of connections. The average human brain has over 80 billion neurons in your brain, and all of those neurons have thousands of connections, resulting in trillions of connections. What this image here is supposed to show is a completely fictional visualization of what brain activity could look like, as we are not able to see electricity. But it's meant to give you an idea of what we're trying to interface with through this technology. So before I'm going to tell you what's new about what this field is able to bring to the table, I'm going to talk a little bit about what is currently available to our veterans who come back, who have had limbs amputated or have had some sort of paralysis. So here is an example of one technology that interfaces with prosthetic devices. And the primary way that this technology works is that the user is able to control the prosthetic device through some other ability that they currently have, such as using their feet to control the arm. So if you had a prosthetic arm, they could actually move their foot backwards and forwards, left and right, and that would control the position of the arm. This is obviously non-ideal because walking around, you would never be able to use that system. And it's also very, very counterintuitive to move your foot to use an arm. There's another type of technology that's even newer, and this is called targeted nerve reinnervation. And this technology will take nerves that were controlling a person's severed arm or legs, and try to connect them directly to a device, monitor those nerves that were in the arm or in the higher up in the shoulder, and try to use those exact nerves to actually control the arm itself, or if it was a lower body amputation, then it would be the leg. The only problem with this is that not everybody who has these kind of traumas, these injuries, has these nerves that are left over. So that it doesn't apply to everybody. It's not universal. We're leaving some people out with this type of technology. It has a lot of benefits over the other type, where you're using something that is completely counterintuitive, but it's still not exactly what we're looking for. So the idea that we're going to do, that neuroengineering is really pushing, is that we can actually listen to the brain. The same way that your physician may listen to your heart or may listen to your lungs, we can listen in on what the brain is saying and what you're thinking, and try to use that communication to control a device. So if we're trying to listen to the brain, we have to know where on the brain are we really trying to listen to? What pieces matter when we're dealing with these types of movement disorders? And what this diagram is meant to show is a cross section of the brain that is called the motor cortex. And this is an area of the brain that controls all of the movements or almost all of the movements that you've ever made in your life. Certain things like reflexes are not taken into account with this section. But you can see here with this top section here is called a homunculus. And the right side shows you what section of this cross section of the brain controls different parts of your body. So for instance, if we had somebody who had their arm amputated, we would want to be listening in on this region here that deals with the arm, the elbow, the wrist, the hand, and the fingers. So if we could listen in on that and be able to translate the neural signals into a meaningful control command that could be used with an arm, then we could provide abilities back to these patients, to these veterans that they've lost. So now, so we know where we want to listen. Now the question is, how are we going to listen? And so what we're seeing here is a very small, what is called a microelectrode array. And this is a device that is made out of silicon, and it is literally 100 tiny little needles that are gently touched onto the surface of the brain and connected to a wire bundle here that allows the electrical signals of the brain to be transferred to the device. That wire bundle is currently connected to something that we call the pedestal, and this pedestal sits on top of the patient's skull, and the skin is closed around it. So while the electrode array is placed directly on the brain, the pedestal remains on the skull, and that allows us, that gives an input that we can grab those signals from the brain. So this just gives you a visualization of kind of what that system would look like. So we have the microelectrode array on the brain, and we have a pedestal up here on the top. So now what I'd like to do is play a video that gives a demonstration of a demo that we recently released. And what this is going to show you is...
this paper, 2 people with tetraplegia, and there's 2 people who were...
What this is going to show you is where the current state of technology is, and show you what we're currently able to do with this field of
a prosthetic or a robotic arm, simply by thinking about the movement of their own paralyzed hand. And they did that using the investigational brain-gate neural interface system. So they thought about using their own arm and hand as though they were reaching out themselves with their own limb, and the robotic arm moved much the way their own arm would have moved. One of the long-standing questions, not only in neuroscience, but in neurorehabilitation, is whether the cells in the motor cortex and other parts of the brain, whether they continue to function the same way years after that original injury.
It is possible for people to use their thoughts to control devices, either a computer or a robotic arm. The way that happens is that we implant a tiny sensor, just about the size of a baby aspirin, just into the surface of the brain, and that sensor pick up the electrical impulses from a bunch of neurons. And each of those little neurons are like radio broadcast towers, putting out impulses. And when they get to the outside, a computer translator converts the pattern of pulses into something that is a command.
One of our participants was able to do something that, when all of us saw it for the first time, gave us all pause. She reached out with the robotic arm, she thought about the use of her own hand, she picked up that thermos of coffee, brought it close to her, tilted it towards herself, and sipped the coffee from a straw. And that was the first time in nearly 15 years that she had picked up anything and been able to drink from it solely of her own volition.
There was a moment of true joy, true happiness. I mean, it was beyond the fact that it was an accomplishment, I think an important advance in the entire field of brain-computer interfaces, that it was really a moment where we helped somebody do something that they had wished to do for many years. This is the culmination of more than a decade of work, beginning with science at Brown University.
And I'm just going to put it there. So this was relatively recently. This happened over the last couple of years that this demo was done. And so this really right now is the leading technology for this type of field. However, what I'm going to jump into now is to tell you everything that's wrong with it and why it's currently not being used to help our veterans. So here you can see this great picture. You know, she just did something that she hasn't been able to do for about 15 years. You can see the happiness. But there's another thing here that might jump out to you, and that's this connector up here. This is the connector that hooks up to the pedestal that is mounted on her skull, and you can see the wire coming out here. And this wire is connected to a giant card of computers.
Oh dear God, we didn't see that.
The translation from the electrical signals of the brain to something that we could actually use to control something is very complicated. And so right there you can already see 2 big problems with this technology to be used by patients in their day-to-day lives. First of all, they're currently tethered to a system through wire, and the system itself is massive. So this is what our lab deals with, is trying to take these two problems and engineer solutions to them to push this technology closer to something that may help people in their day-to-day lives. So the first way that we did that is we said, okay, well, we got to cut that tether. We got to get rid of that. We got to get rid of that wire to the system. And so we designed two different devices here that would allow a patient to use the exact same system but without that wire. The first is a system then to retrofit the current pedestal, which means that this is just a device that screws onto that same pedestal and wirelessly broadcasts the data. The second one here shown is a fully implantable version. And the beautiful thing about this one is that it allows us to fully close that wound. There's no longer an open area of the skin that could be prone to infection or something that you could hit against the head. But this is a fully implantable version with a rechargeable battery that uses wireless charging to perform the exact same functionality as the current wired system. So here we can see a quick animation of what the fully implantable system looks like. You can see the bed of needles here that are used to listen to the brain signals. It's connected through this gold wire bundle to a titanium device that houses all of the electronics for the system. And this device was completely customized, custom built by our lab. The device itself contains a rechargeable battery that is charged through what is called inductive charging, the same way that you might get a wireless charging system for your cell phone. This is the exact same technology. So you can see that there are the custom circuit boards inside and the rechargeable battery as well. So this implantable device, once eventually when it gets approved for human use, would be mounted to the skull the same way that the pedestal is, and the electrode array would be placed under the skull to listen to the brain. However, like I mentioned before, the best thing about this device is that we're now able to fully close the skin and allow the wound to truly heal. So now getting back to what the other problem was, which was this massive cart of computers. And now we're getting into more of what my personal specialty is, which is taking this giant thing of computers and shrinking it down into something that looks like your cell phone. Something that you could put in your pocket and take with you, but still has all the computational capabilities of this system. So this is a project that I've been working on since I got to Brown, and the basic idea is that we're using these chips that are really truly amazing chips, and I'm not going to go into the details of those, but let's just say that it's able to do hundreds or thousands of times more computations that you'd be able to get out of a regular computer. So this is bleeding edge technology. This has only been released over the last 2 to 3 to 4 years in that area. So this really is new, which is why we haven't seen it used for applications like this yet. But the idea is that we can use this type of chip and shrink it down to the bare necessities of what we would need for this system, to a device that would literally fit in your pocket, that a patient could take with them on their day-to-day lives. So the full system here that we could see with this fully implantable version and a smartphone-like device that could that is wearable on the user would allow for a fully wireless and fully portable system that a patient could actually use in their day-to-day lives. Now, here is an image kind of showing that entire system in play here. I never understood why my bosses told them to put the arm on the table. But the basic idea being here that you have an external device that the user would like to control. They have a device implanted in their head that reads their thoughts, a device that translates those thoughts into what the command for the arm, and then is able to control that device directly, all using wireless technology, all in a fully portable system. So now now that we're able to listen to the brain, and if we were able to do that perfectly and control robotics perfectly with that technology, that would be amazing. But there's still one other half there that's missing. You know, it's not just about being able to move your arm. It's, can you feel your fingers? Do you know what you're holding? Do you know how heavy that thing is?